All right, this is for CP Physics on Tuesday, December 1st, 2020, a warm-up problem doing conservation of energy and conservation of momentum simultaneously in a one-dimensional, perfectly elastic collision. The made-up problem consists of two balls. Ball A has a mass of 20.0 kilograms and is initially moving at 10.0 meters per second to the right. Ball B has a mass of 15 kilograms and is initially moving 5 meters per second to the left. They have a head-on, perfectly elastic collision, and the task is to determine the final velocities of the two objects after they collide. The first principle is conservation of momentum, because no matter what kind of collision it is, momentum is always conserved. The sum of all the momenta before they collide is equal to the sum of all the momenta after they collide. The formula for momentum is mass times velocity. In this case, 20 kilograms times 10 meters per second is 200 kilogram meters per second. 15 kilograms times negative 5 meters per second is negative 75 kilogram meters per second. 200 minus 75 means the total momentum before they collide is 125 kilogram meters per second. After they collide, mass A, the 20 kilogram mass, is going off at some unknown final velocity, which I'll call VA, velocity of A after they collide. After they collide, the 15 kilogram mass goes off at some unknown final velocity VB. So total momentum before they collide is equal to 20 kilograms times VA plus 15 kilograms times VB. The second principle that we're going to use is conservation of kinetic energy. The sum of all the kinetic energy before they collide is equal to the sum of all the kinetic energy after they collide. And the formula for kinetic energy is 1/2 mv squared. On my calculator, 1/2 times 20 is 10. 10 times 10 squared is 100. 10 times 100 is 1,000. So I have 1,000 joules of kinetic energy from ball A before they collide. For ball B, it's 1/2 times 15 kilograms times negative 5 squared. The minus sign will cancel out, and I get something like 187.5 joules. Adding those two quantities together, I have 1,190 joules is the total kinetic energy before they collide. After they collide, it's 1/2 times the 20 kilogram mass times its final velocity, VA squared, plus 1/2 times the 15 kilogram mass times its final velocity, VB squared. I have two equations, two unknowns. I'm going, well, first as a comment, this kinetic energy equation is a conic in the shape of an ellipse. This conservation of linear momentum equation is a straight line curve. They will intersect at 2 points. One of the intersections will be the original values before they collide. The second intersection is the after conditions that we're interested in. So one of these is before, one of these is after. To prepare for substituting one equation into the other, I'm first going to divide the momentum expression by 15. That will make the coefficient a 1 in front of one of these velocities. So 125 divided by 15 is 8.333333. 20 divided by 15 is 1.333333. and 15 divided by 15 is 1. So the momentum equation becomes simplified in a sense. 8.333 equals 1.333 VA plus VB. Rearranging to solve for VB, I have VB equals 8.333 minus 1.333 VA. I will substitute this expression for VB into the kinetic energy expression. Before I do that, I see I have a 1/2 here, a 1/2 there. I don't like those 1/2s, so I'm going to multiply the entire kinetic energy expression by 2. When I do that, I have 2,375, because I didn't round it before I doubled it, is equal to 20 VA squared plus 15 VB squared. I'm now ready to substitute this here. I suppose I could have left this as a fraction, and that would make this thing 125 over 15. This thing would be 20 over 15 or 4 over 3. I probably could have simplified this thing down, but I didn't. I'm doing it in decimal form because I know I'm going to use my graphing calculator afterwards. I have to square this expression. To square it, I'm going to use FOIL, meaning I multiply the first two terms, the outer two terms, the inner two terms, the last two terms. After that, each one of those 4 terms will be multiplied by 15. But first, using the calculator, it's also possible I might be able to solve this problem directly on my calculator. Oh dear, what kind of day am I going to have when it says my calculator battery is low and needs to be charged? Let me think about that for a moment. I'm actually going to pause. All right, that only took a few seconds. Got a charging cable, it's plugged in, I'm happy. I'm now going to proceed with, I was saying I could cheat and just put this equation into my graphing calculator directly as a y equals expression, and this one is a y equals expression, graph the two, and look and ask it to find the intersection. But I'm going to do things kind of not so simply. So I'm going to take 8.333 and square it. I get 69.44 minus 8.333 times 1.333. That's 11.1, but I'm going to do that twice, once for the outer two, once for the inner two. So I'm just going to double that and say minus 22.22. And for the last two, a negative times a negative is a positive. 1.333 squared is 1.777. And I didn't put the variable here. So this is minus 2.22 VA plus 1.777 VA squared, still all in parentheses. There. If I haven't screwed up too badly, I next distribute the 15 First term becomes 1042 minus 333, sure, VA, plus 26.66 VA squared. Now I combine like terms and simplify. 20 VA squared plus 26.66 VA squared is 46.66 VA squared. I'm also going to write this in standard form for a quadratic equation. Minus 333 VA I'm going to subtract 2,375 from 1,042. I get minus 1,333. This is a quadratic equation. You might recognize it. Ax squared plus bx plus c. And we need to solve for the two roots. One of the two roots will be 10. I'm going to cheat now and put this into my graphing calculator. Instead of doing the quadratic formula by hand, I'm going to type this in. Well, when I try to graph it, I see a vertical line to the left of the origin. And I say, oh, I think here's a vertical line just coming up on the very edge of my screen. So I'm going to change my window. Let's go from negative 20 to positive 20 by 2's. And for y min, oh gosh, let's go like negative 200 to 200 by 40's. So this is a big enough window that you can tell the way it drew it that it is a parabola. Its vertex is way out of sight, somewhere far below negative 20. What we're interested in are the two locations where it crosses the x-axis. So I'm going to pose the question. Anyone think they have the solution already? And I'm not seeing anyone with it. I'm going to claim that the solution on the right is the original value 2, 4, 6, 8, 10. Sure. This intersection, this root is at VA equals 10 meters per second. And that's the velocity that ball A had before they collided. The second root is negative. And so that means after they collided, ball A actually bounces off to the left. It doesn't keep rolling to the right. I'm now going to cheat and ask the calculator to go find this value. Second, calculate on a TI. Let's find the 0 of it. I'm going to make that my left bound. I'll make that my right bound. And I can't really pick something in between, so I'll leave my guess as here. And boop, there is the answer. Velocity of A after they collide is negative 2.86 meters per second. Oh man, there's the 3-minute timer. What I'm going to do is pause this recording. Okay, I'm going to just resume and finish this one off. So if the velocity of A works out to be negative 2.86 meters per second after they collide, then figuring out the velocity of B would be 8.333 minus 1.333 times negative 2.86. And so I get velocity of B is 12.1 meters per second. 12.1 meters per second.